Okay, hi everyone. I hope this video finds you well. So today we are going to talk about algorithms. So what is an algorithm? So let's take a look at problem solving practice. So suppose we have this list. It's a number list. We have the numbers 10, 3, 5, 9, 2, and 13. So let's run a simple command as if it's for 5 to 6 years old child to sort the list of numbers from the smallest to largest. So the possible solution for that is going to be to create a new list that is empty, then find the smallest number in the old list, add a smallest number to the end of the new list, and repeat those two steps, 2 and 3, until no more numbers in the old list. Now, another solution would be exactly the same, but we add step 4, which is cross the smallest number from the old list, and then when you repeat steps 2 to 4. So let's apply that. So we are going to have something called smallest. And this is one storage location that we are going to use to store the smallest in our list. And here is the new list, the empty one. So we're going to start from the first number. So is 10 the smallest so far? Yes. So we put it in the smallest. Then we compare what's in the smallest with the next number in the list. So is 10 smaller than 3? Now if yes, then keep it. If 10 is not smaller than 3, then put the 3 in the smallest. So that would be 3. Then do exactly that with the rest of the items. So is 3 less than 5? Yes, then keep it and skip the 5. Is 3 less than 9? Yes, keep it and skip the 9. Is 3 less than 2? No. So put the 2 in here. And now we replace the 3 with 2. Is 2 less than 13? Yes. Keep it and skip 13. Do we have any more numbers or any more elements? No, we don't. Okay, so we take the smallest and put it in the old list. So 2. Then we do that all over again. So we cross the 2 right now, right? And we start with the 10. Is 10 smaller than 3? No. Then we replace that. So replace the 10 with 3. 3 and 5, keep the 3. 3 and 9, keep the 3. 3 and 13, keep the 3. Do we have any more elements? No. So 3. Now keep doing that. After we cross the 3, you keep doing that 10, then 10 and 5, and eventually it's 5. Now we cross the 5, then 9, then the 10, and finally 13. Now we followed this one, right? We followed this one. So something that we have done, which was an algorithm within the algorithm we just used, is to find the smallest number. To find the smallest number, what we have done is, 1, we created a space or location, memory location called smallest. We put the first number into smallest. If the next number is smaller than the smallest, then we copied that number into the smallest. We repeated step 3 many times until we get to the end of the list where there is no more numbers. So the smallest number from the list should be written into a space called smallest. So eventually when we ran out of numbers, what's in the small list is going to be the smallest number of that list, and then we add it to the empty list. This is what we have done, right? So we had an algorithm within an algorithm. So if you're in face-to-face class, I would ask you, who is this algorithm, the carrot and the stick, is named after? Now, I'm going to give you the answer. You can pause the video and look for it. Then you come back to see if your answer is correct. Assuming you paused the video, you looked, and then you came back, the algorithm, this one, the carrot and stick, is named after the philosopher Jeremy Bentham. So you can think of the algorithm as a recipe, right? You have ingredients, and then you have the algorithm to deal with these ingredients, everything in a specific amount, and one thing with another or after another, right? So you have to follow some exactly outlined steps. So basically it's a plan to get something done, right? So if you looked at my slides, I'm going to show you this slide because I added some notes to you about the South Park character, the Cartman, because he lays out a 4-point plan for startup success. Startup, cash and salad, bro, down, right? So basically, what you have seen as a child, the 4-point plan, is basically an algorithm. Going back to our slides, so an informal definition of the algorithm. It's basically, this is the informal again, because we have a formal one you have to memorize. The informal definition is a set of rules that precisely define a sequence of operations. So this would include all computer programs, including programs that do not perform numeric calculations. So generally, a program is only an algorithm if it stops eventually. An infinite algorithm is not a good algorithm. An infinite program is not an algorithm in the first place. So even if we are not doing any numeric calculations, and if you say a program is an algorithm, then you should know that we could have many algorithms within that algorithm. So our definition, the one we are going to call the formal definition of an algorithm, is the definition that follows few steps. Basically 4 steps or 4 major points. A well-ordered collection of unambiguous, effectively computable operations that produces a result and holds in a finite amount of time. So basically, our definition of an algorithm is 1. A well-ordered collection. 2. Of unambiguous. 3. Effectively computable operations. 4. That produces a result and holds in a finite amount of time. So, putting that together, that will be a well-ordered collection of unambiguous, effectively computable operations that produces a result and holds in a finite amount of time. So, why are these steps required? So, to know why these steps are required, you have to explain each bullet of these. So let's start with the well ordered. So since an algorithm is a collection of operations or instructions, we must know the correct order in which to execute the instructions. The order is very important. It's like you cannot get dressed first, then take a shower. You have to take a shower, then get dressed. Right? And so on. So usually the order matters a lot. Unambiguous. So each operation in an algorithm must be clear enough to be acted upon. So I can ask you, sort these numbers from smallest to largest. Now you know that you need to sort the number, arrange these numbers from smallest to largest. So if I ask you sort the numbers, then you would ask me for more clarification, like is it ascendingly or descendingly? Smallest to largest or largest to smallest? So a computer needs more details to sort numbers. You cannot give a computer ambiguous details or let's say ambiguous orders to perform something. So the computer must be told how to, for example, search for the smallest number, find the smallest number, compare numbers, putting that smallest number in an empty list, not to visit that exact number again when you look for a smallest number, or you will be in an infinite loop, right? So effectively computable operations. Each operation in an algorithm must be doable. You cannot ask the computer to do something that is not being doable and expect a result. So suppose you're given an algorithm for planting a garden where the first step introduced to you to remove all large stones from the soil. So this instruction may not be doable if you don't have the right equipment, or if there is a 4-ton rock buried just below ground level and you don't have the right equipment to do that, or you just only have a shovel. That won't be enough. So for computers, many mathematical operations such as division by zero or finding the square foot of a negative number are also impossible. So you should handle those things and you should think of them when you're making an algorithm. So the algorithm produces a result. So at a basic level, an algorithm is a set of instructions for solving a problem. So if it's produced no result, how could you know it solved the problem? So unless an algorithm produces a result, we can never be certain whether our solution is correct or not. So you should produce a result. It doesn't have to be a mathematical result, a result based on calculations, sometimes printing something, right? So algorithms hold in a finite amount of time. So to be meaningful, the algorithm must hold and produce a result. An algorithm that does not hold may or may not produce a result, which is one of our previous requirements. So once again, if it's run forever, how could we verify it solves the problem? Solving a problem is part of the basic concepts of an algorithm. Having a result after the solution of the problem is critical, because this is how we know if we solve the problem or not. So let's talk about key points from this lecture. That was a short lecture about algorithms. At a high level, it's a plan to solve some problem. An algorithm is a set of rules that precisely define a sequence of operations. Now, yes, this is the informal definition. The computer science definition, the formal definition in our eyes, computer scientists, is a well-ordered collection of or unambiguous effectively computable operations that produces a result and holds in a finite amount of time. What you need to do, you need to explain what an algorithm to two different people. Be sure to give us simple examples to help them understand. Include the key requirements of an algorithm and why they are important. And always think about the goal of these assignments and why you should be able to do them effectively and be good at explanation assignments. That said, have a great day and see you in another video.